Hello. Hi, so I'm Thomas. I want to tell you about incremental bidirectional typing via order maintenance. This is a very fruitful collaboration between my lab, the Future of Programming lab at the University of Michigan, and our collaborators at the University of Utah. So we learned how to apply the order maintenance data structure to great effect in our programming language problem. And my hope is to give you that tool to put in your tool belt in case it could ever be useful to you. Okay, so what is our problem? Our problem is live programming. And for the purpose of this talk, that means programming with continuous editor services. So editor services could be, for example, syntax highlighting. You see inferred types. The red squiggle is a localized error. All these are editor services. We're interested in kind of those last two, so type checking and error reporting. And continuous means unfailingly. In all editor states, we want this feedback, even if there are errors, syntax errors, type errors, etc. And also quickly. So we want this to be efficient. Actually, we have another constraint. We're interested in live programming at scale. So this is from one of the keynotes, or it was referenced in one of the keynotes. This is a GitHub repository of TypeScript type definitions. So 34 million users and over 17,000 collaborators. Software is collaborative and very large scale now. But kind of this picture exists in a different world from that screenshot of the editor services. Right? So the place where we collaborate with our code doesn't have those services. We have to pull it locally. But we envision kind of a computational commons. So imagine a Wikipedia-sized program that everyone can be working on together with live feedback. So that's our technical challenge. And it's hard, right? So if we want live programming, we want fast editor services, fast type checking. And if we're at scale, we have large programs, but type checking is at least linear in the size of the program. So what do we do? Well, instead of actually type checking every state of the program, every version of the program from scratch each time, no, we can't do that. Our key insight is to observe that most changes to the program are small. Most of the program is unchanged from edit to edit. That means we can reuse typing information, hopefully most of it. And this is incrementalization. This is exactly what it means to incrementalize a computation. So that's our setup. And how might that work? So actually, what do we want out of this analysis? So if we have our syntax tree here, we imagine our output could have the inferred type. So the upwards arrow means the inferred type of a subexpression, the synthesized type, and analyzed types, the expected type of a subexpression given the surrounding context, and also some kind of localized type errors. So this is the data, the marked and annotated data that we want to incrementalize the calculation of. And these actually work very nicely together. A bidirectional type system where you have checking and inference works very nicely with error localization. And the formal theory for that we use is the marked lambda calculus, the theory of which was published at POPL 2024. Okay, so how might we incrementalize the calculation of these attributes? Well, let's imagine an edit comes in. So I've displayed in gold adding a node to the tree. This kind of represents wrapping a subterm in a unary term constructor. So step one of our DIA is to mark that changed part of the program as dirty. Dirty meaning that a change has occurred, something is out of sync, something's out of date. And then you find that dirty part of the program and calculate the local change that needs to occur. You calculate the immediate effects of that change in terms of the types and errors. And then the neighbors that were changed, you mark them as dirty because they may be out of sync with their neighbors. And then you repeat. So at each stage, you pick a dirty part of the program, locally calculate its updates, propagate them outwards one step, and continue. And when does it stop? Well, it stops if you recalculate, say, the type of a term, and actually it didn't change from time 1 to time 2. If it didn't change, then it doesn't need to be marked as dirty because it's not out of sync with its neighbors. So eventually this process terminates, hopefully. And we formalize this system for the bidirectional marked lambda calculus. And we proved 3 major metatheorems that I'd like to share. The first is validity, which basically states that the incremental version of the algorithm agrees with the from-scratch version of the algorithm. It's valid with respect to our base type theory. And that corresponds to this commutative diagram, which I won't explain in detail, but it says that if we apply this action and then propagate all updates until we can't anymore, we'll get the same result as having retype checked the program from scratch. Convergence states that you can apply, so I specified a non-deterministic process of propagating updates. And we can guarantee that no matter which order you choose to propagate these updates, you'll obtain the same result. And actually, it's better even than that. You can even interleave actions, edit actions that change the tree with update steps. You don't have to wait for the end of update propagation to make an edit. And this is very important for scale and liveness, because as the program grows large, you might have to take a lot of update steps to account for a change, even if you're incrementalized. And you don't want editing to be blocked during that time. You want the editor to remain live. So this theorem validates that as possible and valid. And then finally, termination. Update propagation terminates. So all of these theorems are mechanized in the Agda proof system. Okay, but there's a couple of problems with the picture that I've just painted. The first is the order of updates. So it was a non-deterministic system, but it really does matter in which order we choose to step these updates. So there's kind of an upstream and a downstream, logically. And if you step updates that are further downstream, that effort will be wasted, because then the upstream calculations will come along and overwrite them anyway. So it's really important to prioritize the further upstream changes. And it's not clear how to do that, given what I've said so far. And there's another issue, which is that type checking isn't local. So I conflated the logical neighbors, so the immediate ramifications of an update, with the AST neighbors. But that isn't always true. It's mostly true in our bidirectional system, but it isn't true because of bindings, right? So the type of a variable depends on the local information at its binding site. And on paper, we kind of use the context in our formal rules to make that local with our syntax-directed rules. But we don't want to be carrying around the whole context. That is not acceptable for incrementality. So we have some kind of non-local information propagation. So, well, we can kind of make it local by just adding pointers, adding structures to our tree between bound variables and their binding locations. That is to make this an abstract binding tree. And that is what we do, but it introduces another problem, which is how to maintain these bindings. So this is what it might look like. We have a variable x, and it points to the place where it's bound. And that question mark represents an expression hole. And if an edit comes in that places another x variable in that hole, then to maintain these binding pointers, we need to find the place where x is bound. And this is a non-local computation. The obvious way to do that would be to walk up the spine of the tree. You look at x's parent and its parent and so on until you find a binder for x. But that requires walking the entire spine of the tree, which is unacceptable to us because it could be linear in the size of the program. We don't assume the program is balanced. So can we get even more incremental than that? So if we don't know where to place x without an unacceptable computational cost, this is the binding problem. Okay, so I just presented two issues, the order of updates and the binding problem. And that's where the order maintenance data structure comes in. So here's how this will help us. Well, the key idea in our data structure is to augment our tree with order intervals, like this, representing a kind of circumfix order. It's like pre and postfix at the same time. So the interval for a parent, the left endpoint comes first of the parent, and then the intervals for the children, and then the right endpoint of the parent. So ancestry, the parent interval contains the children intervals, and the sibling intervals are disjoint and ordered. So how does this help? Well, it shows us how to prioritize updates that flow up and down the tree. So those flowing down the tree use the left endpoint because that comes first, that's further upstream. And updates flowing up the tree use the right endpoint. And then for the binding problem, for the binding problem, it's clear how to check ancestry of one node from another efficiently. You just compare the endpoints. But we actually need to find the lowest ancestor that is a binder. And I won't go into how to do that, but we can do it in polylogarithmic time using a balanced ordered tree of all the binders for x for each name in the program. Okay, great, but how do we actually maintain those intervals? Where does that data structure come from? Well, in the 80s, there's this famous paper that introduces, that presents two implementations of the order maintenance data structure. So I won't tell you how the data structure works, but I'll show you the interface. The order maintenance data structure maintains a finite set of ordered elements, and it supports an insert operation. So I'm kind of showing you how that manipulates the data structure over time. The insert operation inserts a new element directly after an existing element. You can also delete elements in the order. And of course, you can compare elements in the order. And if cleverly implemented, each of these operations can be O of 1 time, amortized. So how do we use that to maintain our intervals? Well, say we have a structural edit action that comes in and wraps this subterm in another. So it inserts a node. We can construct the interval by calling insert. The arrows represent calls to insert. The left endpoint of this interval is inserted directly after the left endpoint of the parent, and the right endpoint similarly for the right endpoint of the child. And if we didn't have a child, so we're adding a new leaf node, we can insert to get the left endpoint from the parent, and then insert on the new left endpoint to get the new right endpoint. So these are just 2 examples, but the technique generalizes to all of our actions. And since each of these operations is efficient, each insert operation in comparison is efficient, then we can maintain these intervals efficiently. OK, so that is our system for incremental bidirectional type checking. And how does it compare with prior work? We're not the first people to tackle this problem. Well, lots of language implementations have some kind of incremental compilation or type checking. But usually this is at the level of the module or the file, where ours is at the level of individual AST nodes. And also some of this is not very well documented. So we're presenting a formal mathematical theory. And our idea of propagating the dirty information along is based on adaptive functional programming. So this is kind of one general approach to incremental computations, along with memoization. And as for type checking in particular, there's an interesting line of work that uses data log to automatically derive incrementalized type checkers from their non-incremental specifications. But it's hard when you do this to get the really fine-grained incrementality. And even in the best case, you still have to kind of traverse the spine of the tree without this order maintenance trick. And the order maintenance trick it comes from the work on actually browser web page layout incremental computations from our collaborators at Utah. All right, thank you for listening to the talk.
We have time for a question or two. Come on up to this mic or that one. Yep.
Thank you for the talk. So I worked on this data log stuff, and maybe you can help me again understand why in the data log work you think you need to walk the spine, but now you don't. So first in data log you also don't need to walk the spine. You just do that initially, and then you remember, right? And you just need to propagate along the hops that are the binders. Is that similar to this order maintenance trick you're using?
So yeah, maybe my understanding is imperfect, and I'd love to hear more about it. So yeah, I think we maintain the binding structure. So there is this notion of remembering the order, but calculating the binding structure initially, we don't need to traverse the spine because, well, I actually didn't describe how exactly to do it, but I claimed that we can calculate the lowest ancestor, the binding location of a variable in polylogarithmic time, using a global balanced tree of all the binders for x. So we don't need to traverse the spine at all, even at the beginning. Did I understand your question correctly?
Thanks.
So while this question's being asked, let's go ahead and swap computers.
Sure. Thank you for the talk. You did this in Agda, so you had to build the order maintenance data structure into Agda, or you have an implementation